Welcome to the video lecture series for Texas A&M University course Math 152. Today we will look at section 7.4, Work. You can find the accompanying handouts at bit.ly/Raelene Math 152. Let's begin. As a warm-up, determine the work done by the weight force of a block of mass m that slides down a ramp h meters long, whose angle of inclination is theta. Set up a coordinate system and the polar components of the vectors carefully before calculating work. Well, we know that work for a constant force and a constant displacement is calculated as the dot product of force with displacement. And the polar form of this is FD cosine theta, where we refer to theta as the angle between the vectors. I'm just going to put angle inside here, because when we draw the picture, if we have a ramp angled at theta in here for the angle of inclination of the ramp, and we start to draw some of our vectors, we may not have the same theta that we use for the definition of the polar form of the dot product. So we have a block. The block has mass m, and as a result there's a certain weight associated with that block, and the weight force is Fg. We also have a normal force acting perpendicular to the surface of the plane. However, we're not interested in calculating the work done by anything except for the work done by the weight force. So the normal force does not contribute to the work calculation we're doing in this example. We also have a displacement, and we happen to know that the ramp is h meters long, and the displacement vector is in the direction of the ramp towards the left, going down the ramp. So what we can see is a coordinate system here. We can take the origin to be the center of the block, and we can take the direction of the ramp to be the x-axis, and perpendicular to the x-axis is the y-axis. So we can redraw this in what we call a free body diagram. A free body diagram means that we don't have the real life diagrams of the block or the ramp. And so I'm still going to keep my x and y axes rotated for now and just redraw the vectors. The vectors that I'm interested in for the forces acting on the object are only the weight force, and I will actually use my displacement vector here, which is not really a force vector, to go in the free body diagram. And I'm going to put my displacement vector in yellow. And then the displacement vector is called d. And we want to know what the angle is between these two so that we can calculate the dot product. Well, by geometry we can see a similar triangle right here to the triangle of the actual ramp. And as a result, I'm just going to make that a little bit tidier. As a result, we can see that the angle theta lies in here. And since this is a right triangle, we can see that the angle here between the displacement vector and the weight vector is not theta, but it is the complement, pi by 2 minus theta. So we have to be careful when we are using formulas that we don't just use the same symbol that might be given in a problem that represents something other than what the symbol is used to representing. So it's better to think of the formula verbally. Magnitude of the first vector times magnitude of the second vector times the cosine of the angle between the vectors, as opposed to memorizing a formula, an algebraic formula, FD cos theta. Okay, so now we're ready to come up with the polar components of the vector. Well, we're going to use the polar component form of the work. So therefore work is equal to the magnitude of the first, which is going to be mg, times the magnitude of the second, which is a length of h, times the cosine of the angle between, which is pi by 2 minus theta. And by the cofunction identity, cosine of an angle is the sine of the complementary angle, and the complementary angle to pi by 2 minus theta is the angle that you would add to it to get 90. In other words, sine of theta is the expression for cosine of pi by 2 minus theta. And so the work done is mgh sine of theta in joules. Well, in general, we can define work as the amount of energy, which is a scalar quantity measured in joules in the SI system, which is transferred to an object by a force that acts on the object and causes it to be displaced. In the case of the normal force in the previous example, the normal force was perpendicular to the displacement. And so if we had put the 90 degrees for the angle between the displacement and the normal force, we would have gotten that cosine of 90 degrees is 0, and as a result, the normal force did no work on the mass on the block. So it's really important that we know that the force has to contribute to the displacement of the object in order for work to be done. So let's let W be work, F vector be force, S vector be position, and delta S vector be displacement while t is time. So if we have a path from point A to point B that the green block is going between through action by some force, and it's causing some it's a measurable force but an infinitely small amount of displacement because we use green for the displacement or blue, because the direction of the block is constantly changing according to the tangent to the curve. We can see that we are going to take really small displacement vectors, or like delta x's, but it's on an angle, so we're going to use delta s, which shrinks so that we can actually accumulate for every different point in time. We need to be able to determine what is the angle between the force vector and the displacement. Now we may actually have different amounts of force for different locations of the block. For example, here we'll have a block, we will have a displacement vector that may be here, and we may have a force that is completely different. Maybe the force is acting here and it's really long. And so we can see that there could be a variable force. So in general, the vector force may vary in magnitude and direction, so it may not be constant. Also, the vector displacement may also vary in both magnitude and direction. Here at least we see that the ds vector is definitely changing in direction because of the path of the curve having different tangents at each point in time. Furthermore, the force and the displacement do not have to be the same direction. As a result, if we want to calculate work, the forms that we've used in the past, namely that work is force times displacement, or force times displacement times the cosine of the angle between them, otherwise known as FD cos theta, F dot D, or the integral of f of x dx, these might not all work. The problem with the first case is that force is constant, displacement is constant, and they are in the same direction, because this is multiplied by 1, which is the cosine of 0 degrees. The problem with the second case is that while we don't necessarily have the force and the displacement in the same direction, they are both constant. The problem with the third case of defining work is that while the force is allowed to be variable, the displacement is not, and we also see that we're multiplying by 1, which again represents cosine of 0 degrees, saying that the force and the displacement, while the force is not constant, the force is parallel or in the same direction as the displacement. So in order to be as general as possible when we are defining work, we are going to have to consider that work is an accumulation instead of a multiplication of a force vector, which may vary, and a displacement vector, which may vary. So we are going to look at possibilities like this. The magnitude and or direction of the force may vary at different points, so the force may be a function of position. So we can call the force F vector of S. I used X in the previous line. Since the force may vary at different positions along the object's path, consider partitioning the path into infinitely many slices of displacement, each that is so small so that the force is essentially constant on that interval. This sounds really familiar with our work with Riemann approximations. And therefore, we are going to let that really small little sliver of displacement, delta S vector, be approximated by ds vector. Only the scalar component of force, remember vector component and scalar component from Calc 1, only the scalar component of force acting in the same direction as the displacement contributes to the work. So that's the idea that we can't have a force perpendicular to the displacement and contribute any work, like the normal force in the warm-up question. So therefore, use the dot product of force and a little slice of displacement to mathematically define a little slice of the scalar work. And then the definite integral accumulates all of the little slices of work along the path of the object's displacement from the beginning to the end, so some lower bound and upper bound of integration to get the net work. So therefore, the general expression of work could be given by work equal to the integral of a little bit of work, which is a definite integral of the variable force vector dotted with the variable displacement. Well, actually what we're doing is taking such a small little bit of displacement that this is now constant. By the polar definition, we can introduce the cosine of theta, where theta represents the angle between the two vectors. So we have theta inside there. Okay, so some special cases we saw earlier of the general definition of work. We saw in Calc 1 that we could define work as a definite integral from some beginning position to some final position of f of s ds. But in this case, the force and displacement are parallel. Another case that we saw in pre-calculus and also at the beginning of Calc 1 is that work is the dot product of force and displacement, but the difference here is that force is constant, where in number 1, force was not constant. We are not allowing, as in case 1, the two vectors to be parallel. In case 1, we said that the angle between was 0 degrees, but in case 2, we are allowing for any angle between the two vectors. And then a really, really simple case, work equals force times displacement. The force is constant, and it's in the same direction as the displacement. That should say displacement, not position. Okay, so some graphical representations of various special cases if we have the force and the displacement in the same direction. If we have a constant force and a certain displacement, then let's consider the weight force. The weight force for objects on Earth over a reasonable period of time is constant. So the constant mg is the magnitude of weight, and if we have, well, let's actually call this a position graph, so this is not displacement, but we could go from some beginning position to some final position, and then if we wanted to calculate the work done, we're really looking at a definite integral. Now in this case, this is nothing more than regular multiplication because we have a constant force. We don't need integration when we have a constant, that's just called multiplication. So here we would end up with mg multiplied by b minus a. We can also see this as mg times a change in position. If this is the weight force, then the work done by a weight force in a vertical displacement, because we're talking about the same direction, we have some kind of vertical displacement of an object, which might be called the height. And so we could see that b minus a might be the height, and this is a very familiar formula for the gravitational potential energy of an object with mass m. Okay, another case is a linear force. So if we have a spring force, technically the spring force is going to be negative kx, and I'll talk about that later, so you should add that in here. But we might be talking about the work done by an object to overcome the spring force, in which case we don't have the negative because overcoming the spring force is in the opposite direction. When we take a look at a linear case of a force, then we can't just multiply because there's not just one force value or force function value, but we can actually just use geometry instead of calculus to come up with the definite integral. So if we wanted to figure out the work from the accumulation here, we could just take 1/2 base times height and we would be done with it. In the case of setting up the integral, we perform the integration as kx squared over 2 evaluated from x initial to x final. And we get this formula. Very often we are going to take, for example, in the case of a spring, we're going to have some equilibrium position, a relaxed length of the spring, which may be, in a later example, 3 meters. But we are going to take that 3 meters and call that x initial equal to 0, because we want to refer to the relaxed length of the spring as the starting position of the spring, which is an initial position of 0 meters. So even though there's an actual length of 3 meters in the spring, we are going to reset that length, if you will, as an equilibrium or relaxed or natural length to be 0. We can take a nonlinear force so that it's not constant nor linear, and we can still perform the accumulation by seeing we're going to have some negative work or negative accumulation, and we are going to have some positive accumulation. And of course we express that with a definite integral. So note that work, because it is an accumulation from a definite integral, can be negative. The sign of the scalar quantity designates whether energy was transferred to or from the object, while the force acted on the object to cause the displacement of the object. We need to have some physics formulas before we proceed. In general, we saw that work is going to be a definite integral of a dot product of a variable force function and a displacement, infinitely small displacement vector. We also need Newton's second law, which says that F equals ma, and we can express it in vector form or as a second order, second degree differential equation, where S represents the position. It's a position function with respect to time. With respect to time. Recall that weight then is a special case of Newton's second law, where we have the force acting in the same direction as the acceleration, is given by mg, where g is the acceleration due to gravity, which is approximately 9.8 meters per second squared. Later on, if you go down to number 6, we can see how this g value of 9.8 approximately has been derived by using Newton's universal gravitation law, which is a law that finds the attracting force or the gravitational force between any two objects. Meanwhile, the weight force is a special case of the general gravitational force between any two objects, because the weight force of an object is the specific gravitational attraction between the object and the Earth. So if we use the general formula and we use the constant g given here, with capital M as the mass of the Earth, which I've given here, and then little m being the mass of whatever object you are interested in determining the weight of. Also, we need the distance separating the two objects, the Earth and the object, and that distance would be the radius of the Earth, which constant is given here. So you should try plugging those in and confirm that you're going to get a g value, a little g value of approximately 9.8, because when you isolate the m from the rest of the expression on the right-hand side, the g capital M over r squared is nothing more than what little m is being multiplied by up here. And so we can see how the general formula for universal law of gravitation between any two objects in the universe actually contributes to the special case between the object m on Earth and the Earth's gravitational force. In number 4, let's talk about Hooke's law. Hooke's law is a law for springs, and specifically Hooke's law is a linear function which is dependent on the length of the spring, or the displacement rather of the spring. If you displace a spring, then if you were to let it go, the force in the spring would cause the spring to accelerate in the opposite direction of the displacement. As a result, we have a negative sign in the formula relating the force, the spring force, and the displacement x. We also have a constant here, k, which is called the spring constant. It's a positive quantity and it's measured in Newton meters. And make sure that we are referring to x measured from the natural or equilibrium length of the spring. One last formula we need for some of the examples we will see is mass density. Rho is the Greek letter measured by mass divided by volume. And so if we wanted to have some specific materials that we are dealing with, we may need to know, to do some work on them, what the mass density is. The mass density of water is 1,000 kilograms per meters cubed. It may be practical to rearrange this equation. We can see that volume is equal to mass over density, or we can see that mass is equal to density times volume. And you can always go back and double check your units. Now, a formula like this, which is ultimately a multiplication formula, is valid only if all of the quantities are constant. So we must be careful that we are using a multiplication formula when we have the quantities are constant. If the quantities are not constant, of course, that's when we introduce a definite integral as a more general version of multiplication or accumulation. Let's take a look at an example from the textbook. I encourage you to read the textbook example first and then take a look at my approach to the question. A tank has the shape of an inverted circular cone with height 10 meters and base radius 4 meters. It is filled with water to a height of 8 meters. Find the work required to empty the tank by pumping all of the water to the top of the tank. The density of water is given as 1,000 kilograms per meter cubed. Well, let's draw a picture. We've got an inverted circular cone. It looks like this. And we have water, not all the way to the top. We have water to a height of 8 meters, and the top is at 10 meters. So I'm actually going to right away put in my coordinate system, and I'm going to put my vertex of the cone at the origin. And so I see here that I've got 10 meters, and here I've got 8 meters. As soon as we have coordinate systems, we should get in the habit of recognizing points and plotting some points. We have a point over here, which is at the end of our line segment connected from the origin, which is at a horizontal position of whatever the radius of the cone is, which is 4, and a vertical height of 10. The question says, if the water is filled to a height of 8 meters, what is the work required to empty the tank by pumping all of the water to the top, so to a height of 10 meters? Well, the water forms a circular cross-section at the top, and we want to take all of the green water. I don't really want to make it green, I'll put it in yellow. We want all of the yellow water to be pumped to the top. So there's going to be a vertical pumping force that will have to overcome the weight force due to gravity of all of the water. The problem is the water does not have a constant weight at each height, because at each height we are going to get different slices of water in cylindrical shell, or rather circular cross sections with roughly a constant height. And so we're going to have a little cylinder slice of water at different heights, and because we have different radius for each of these little slices, the different radius means that we're going to get different volumes for each of these little slices, which means that the lower down slices of water have less mass than the higher up slices of water. However, the higher up slices of water have less distance to travel to be pumped out. So we really have to consider all of these factors when we want to calculate the work. So what we're going to do is focus on a typical slice of water and find out how much the work for that slice of water would be. So we're really going to calculate a little bit of work for a typical slice and then accumulate all of those work slices for all of the little water slices. So we start with something we know. We know that work is going to be the integral of a little bit of work. And this could actually either be a little bit of force times displacement. And the reason it's times and not dot is because the force that the pump will be applying is going to be an upwards force to overcome the force of gravity. So we are going to apply a pump force upwards, and the direction of the displacement is also upwards. And I'm actually going to use S for displacement as opposed to delta S. Unless, of course, we have to look at another consideration, which is that we have a measurable amount of force and a little bit of displacement. Well, if we look at the purple slice or the red slice of water, we see that to go from that height to the top height is a measurable displacement. So we are actually going to go with the infinitely small or little slice of force multiplied by displacement. We don't need to use the dot product because the two vectors are in the same direction, so the cosine of 0 degrees is already 1. So we're going to focus on this formula, which means that we need to calculate dF. So if we take a look at dF, we recognize that dF has to be the force of the pump, where the pump is the same magnitude as the weight force. And if we deal with the magnitude, we have m times g, because the weight force is what the pump has to overcome in order to get the water slice to the top. Let's focus on the red water slice as our typical water slice, which means that we have a point on this boundary line with coordinates called x, y. and that typical slice is located at a height of y. Then we know that any constant can come in front of a limit or a derivative or an integral, also in front of the differential. So that makes that g, which is approximately 9.8 meters per second squared, times a little slice of mass, or a little bit of mass. The little bit of mass is unknown to us because we don't know how much volume we have. And so we need to convert from mass to volume using density. So we know that density is equal to mass over volume, and therefore mass is equal to density times volume. So we have g times a little differential of, or a differential of rho times v. Now for different slices, the density of water does not change, but the volume does. So density is constant, and that can come out in front. So now we're back to a point where we were at before in section 7.2 and section 0.3. We have to calculate dV. And we know that dV can be a little bit of area times a measurable amount of thickness, or a measurable amount of area times a little bit of thickness. And in this case, we see that we have pancakes because we are stacking our water slices perpendicularly to the y-axis, and so the thickness is dy, and we have a cylinder, so the cross-sectional shape is a circle, and so we are going to write this as, I'm going to put it over here, we're going to write this as rho g times a little measurable amount of area times a little bit of thickness, which is dy. I don't like putting it there. I'm going to make it tidier on the next page. So this is rho g area times dy. From here then we need to focus on how to calculate the area. So the area is going to be the area of the typical red cross section. I think I'll put it in green, the green cross section. And so that green cross section has a radius from the y-axis until the point on the edge of the line, which is a radius of x, and we have a cross section of pi x squared. Let me just write it here. Area equals area of a circle, which equals pi r squared, which equals pi x squared. But we recognize that we are going to be integrating with respect to y, and therefore we need to express the area function in terms of y, which means that we need to come up with a relationship between x and y. Well, you can see similar triangles here from the origin to the red slice and from the origin to the top of the cone. Or you can just recognize that there's a direct variation or a linear relationship between x and y. Y is equal to a slope times x plus 0 for the y-intercept, where the slope is a rise of 10 over a run of 4. And 10 over 4 reduces to 5 over 2. But then to isolate x, we get that x is equal to 2/5 times y. So we have that the cross-sectional area for a typical slice is pi times 2/5 of y all squared, where y is the height of the typical slice. So we get 4 pi over 25 y squared. We take that and we substitute it back here for area, and then we take that whole expression and we substitute it in for df. I'll just extend the page rather than go in the next one. So far we have that work then is going to be, we have some constants. We have rho g times 4 pi over 25 times y squared times dy. Unfortunately, we're not done because that expression is just this expression. We still need to come up with s, the displacement. Well, the displacement is purely vertical to take that slice to the top, and we're going from a beginning position for the typical slice of a vertical position called y to a vertical position called 10. So when we want to calculate the displacement is going to be y final minus y initial, and we have 10 minus y for the displacement. So our work integral will be set up as the definite integral with respect to y. So we need to know, where do the water slices begin and end? Where are we stacking them at the beginning and at the end? Well, the first water slice in the yellow shaded water section is at a height of 0 until a height of 8. And so we have all of this expression multiplied by 10 minus y. And once we have it all in there, we can tidy it up and put it in the correct order, and we can take constants in front of the integral. So we're going to get 4 pi over 25 rho times g times the integral from 0 to 8 of y squared times 10 minus y gives us 10y squared minus y cubed, all dy. So we get a polynomial expression to integrate and apply the fundamental theorem. I'm going to do this on the TI Inspire and then check the answer with the textbook. So I'm going to type in 4 pi, first add the calculator, 4 pi over 25 times rho, which is 1000, times g, which is approximately 9.8 or 9.81, times the definite integral from 0 to 8 of y squared times 10 minus y integrated with respect to y. And we get an answer of 3.366 times 10 to the 6. I would be happy leaving all of this 4 pi over 25 rho g as a constant and then only doing the evaluation on the definite integral. So we have this value for work. So you can compare with the textbook example and see which approach you prefer. Starting the exercises, I'm going to leave you to try question number 1 and question number 2 on your own, and we'll start with number 3. The amount of work done by a force to displace an object 12 meters is 52 joules. What was the average force applied to the object throughout its displacement? Well, if we consider that we have force along the vertical axis in newtons, and we have some displacement, or rather position vector, position quantity, axis, called x. I'll just write that this is position along here. Then to go a displacement of 12 meters, let's say that we start at A, and we go until A plus 12. Then the force may be any kind of force. It may be constant, it may be linear, it may be nonlinear, it may be positive, it may be zero. It may even be a discontinuous force in that it has a removable discontinuity or a jump discontinuity. But we know that work is going to be the definite integral. So if the force is something like this, then we could create a definite integral which gives us 52 joules. So we would have some amount of force below the x-axis, or work below the x-axis. Rather, we would have some amount of force below the x-axis and some above the x-axis. And in that case, we would have, let's say that this is 60 joules when we integrate from B to A plus 12, and down here maybe that's negative 8 joules. And so we could see that the work is going to equal 52 joules coming from the fact that we have a definite integral from A to A plus 12 of the force times the displacement. And so that's going to be negative 8 plus 60. This is not very convenient because we want to find the average force, not the variable force. So the average force is the constant force that, or the one force that the variable force would be if the force were constant. In other words, we want to find a constant force that when we multiply it with a displacement of 12 gives us 52 joules. And so we'd have to put a force at a certain height along here called the average force. It's a constant function, so that our accumulation ends up in one step to be positive 52. And so this shouldn't be so hard. Work is equal to the average force times the displacement, and so the average force is going to be the work of 52 joules divided by 12 meters. We can reduce this. 4 goes into 12 3 times, and 4 goes into 52 13 times, and joules divided by meters is newtons. So we get 13 over 3 newtons. There's no need to give decimals or approximate. You can leave the answer like that. We'll talk more about average function value in section 7.5. In number 4, a 5-meter long water trough with equilateral triangle ends, which are length of 3 meters, rests on its edge, so the rectangular water surface is at the top. The trough is full of water. Determine the amount of work required to pump the water, first of all, to the top of the trough. Part B says to a height 1 meter higher than the top of the trough. Let's take a look at those two first. Well, we have a triangular prism and equilateral ends. And when we draw our trough like this, we see that the trough is 5 meters long. And so we have 5 meters along here. And the trough is filled with water. And we want to determine the amount of work required to pump the water to the top. Well, what we're going to do is recognize that the constant length of this is not so important when we are looking at a thin water slice. So we're going to focus on the end of the trough, which is an equilateral triangle, and we are going to make a coordinate system through that equilateral triangle. There are lots of options, but I'm going to put the x-axis and the y-axis. I'm going to put the origin at the bottom of the triangle. So I'm actually going to draw the coordinate system first and put this point at the origin. Okay, so what we need to do is focus on a typical water slice. And since the trough is full, we can choose any height we like. I'm going to choose a height somewhere in the middle to make it look typical. Okay, so here's my water slice. I'm going to take it really, really thin. The reason I'm taking it really thin is because I essentially want the force to be constant, because I don't want to have to deal with variable force in my integral. Well, work is equal to the integral of a little bit of work, which is either the integral of a little bit of force times displacement, or the integral of force times a little bit of a displacement. By taking a thin water slice, I'm going to focus on a little bit of force required to pump. So again, the force of the pump is going to be equal in magnitude and opposite the direction of the weight force of that slice. So this gives me something to focus on. When I look at my cross-sectional end, I don't need to worry about the length of 5 meters going behind into the page, and I just see the cross-section here as a rectangle. Because I am stacking my cross-sections perpendicular to the y-axis, the thickness or the height of that rectangle is a pancake, so I have dy. So now I'm ready to build my df and then substitute back into my definite integral. So I know that df is going to be a little bit of mg because I'm using the pump to overcome the weight force, which is given by mg. The g is constant, and now I need a little bit of mass, which is going to be given by density times volume. Volume is the density is constant, so I get rho g dv, and the dv is going to be given by either a little bit of area times thickness or a little bit of thickness times area. And because I have a measurable amount of area in yellow multiplied by the thickness dy, I'm going to call it a dy for dv. So the area is the yellow cross-sectional area, which is going to be the length times the width. So the length is 5 meters, but I also need to know this distance along here. And that distance, of course, is the same distance here. Well, the reason we have a coordinate system is so that we can plot typical points. And this is a point xy, again, on a line segment. We have a point here, 0, 0, and therefore we should be able to come up with the information in the problem with the coordinates of this point. We are told that we have an equilateral triangle of 3 meters, so we know that we've gone 1.5 meters to the right, and that's called, let's call it 3 halves. And we also have a certain altitude. Now it's worthwhile getting really familiar with your basic triangles or special triangles from trigonometry. This one is half of an equilateral triangle. And so, of course, it is the 30, 60, 90 triangle, because we have 60 degrees in each of the angles for the equilateral triangle. And so if the hypotenuse is A, then the small side is 1/2 A, and the altitude, or the opposite, or the longer of the two legs of the triangle, is √3/2A. So in this case, we have a triangle with a hypotenuse of 3, so the short side is 3/2, which we had already seen, and the long side is √3/2 times 3, so 3√3/2. Of course, you could have just used trigonometry with the 60 degrees up here to find the altitude, or the y-coordinate at the top. So this point is 3/2, comma, 3√3/2. And now we're ready to figure out the area. So this distance from here to here is x, so the width of this rectangle, this yellow rectangle, is going to be 2x, and then the area of the yellow top surface is going to be 2x times 5, and so that's the a value. So we're going to get rho g times 2x times 5 times dy for the little bit of volume. So we have 10 rho g x dy. However, we are integrating with respect to y, so we need to isolate x and substitute it, or rearrange that expression, substitute it in terms of y. Well, the expression that we have to relate x and y comes from the line segment, and we know that y is equal to the rise over run times x again. And if we have y equals rise over run, we rise 3√3/2 and run 3/2. So the 3/2 will reduce, giving us √3 times x. Similarly, that says that x is equal to 1/√3 times y, and we can substitute that there. So we get that the df is equal to 10 rho g times 1/√3 times y dy. Now, we're not quite finished because that's taking care of the df, but we still need to work out the displacement. So in this case, we're considering that our typical water slice, which is currently at a height of y, has to be pumped to the top of the tank to a height of 3√3/2. Because the tank is filled with water, we have water slices all the way from the bottom height of 0 to the top height of 3√3/2. So we want to pump the water in part A to the top of the trough. So this green slice, or this typical cross-section slice of water, has to go from its current position of y to 3√3/2, which says that the displacement is going to be y final, 3√3/2, minus y initial, which is currently height of y. Then we put these together in the integral, and there's only one thing left to do. We need to work out the bounds of integration. Again, what we are doing is accumulating all of the little bits of work for all of the little bits of water slices from the bottom to the top of the tank. So in part A, our water will be stacked from 0 to 3√3/2, and we have to multiply the df times the s. So we get 10√3 rho g y times 3√3/2 times minus y, all times dy. And again, all of the constants, which I will circle, can be brought in front of the integral. In part B, we have a slight change because we are actually going to take the water a little bit higher, 1 meter higher. And so we are not interested in pumping to a height of 3√3/2. We're interested in pumping to a height of 3√3/2 plus 1 additional meter. So the water is still stacked from a height of 0 to a height of 3√3/2. So the water stacks do not change, and therefore the bounds of integration do not change. What does change, however, is our displacement. Our typical water slice is no longer going from y to 3√3/2, but it's going from y to a higher height of 3√3/2 plus 1. So our displacement is going to be 3 root 3 over 2 plus 1 as y final minus y. And that makes the only change in the integral from before to be the displacement part. So the work is going to be still, I'm going to put the constants in front. 10 rho g over root 3 times the definite integral from 0 to 3 root 3 over 2, still the same stacks of water. We don't have water that's higher than the tank. And we are going to multiply y times 3 root 3 over 2 plus 1 minus y for the displacement times dy. And lastly, in part C, it asks what additional work is done by the original pump, which is a vertical pump, to transport water 5 meters to the left of the previous drainage. So the previous drainage is the 1 meter high. So if we were then to go 5 meters to the left, we know that the displacement, the additional work, would have a displacement that is to the left. But the original pump is vertical. And so when we calculate work in part C, we have that the force of the pump is perpendicular to the displacement, and therefore the additional work is equal to 0 joules. Okay, in number 5, we're going to be dealing with springs, so this makes us think of Hooke's law. The equilibrium length of a spring is 3 meters. A 10 Newton force is required to stretch the spring an additional 50 centimeters. We want to find out how much work is done in stretching the spring 5 meters beyond equilibrium. Let's just take a quick look. If we have a string stretched to equilibrium, this is 3 meters here, but we are going to reset 3 meters to a displacement of 0, so that it's only a change from equilibrium which could lead to a positive or negative displacement. Specifically, stretching the spring leads to a positive displacement. Meanwhile, compressing the spring leads to a negative displacement. So in these diagrams, x represents displacement, not position. So it's the difference from equilibrium position, or equilibrium length. And just like in the previous example where we were talking about the pump due to the force due to the pump, we are going to be talking about work done not in the spring, which is given by Hooke's law as the spring force is negative k times x. We could also write that as the force is a function of x, because x is the displacement. So we see that this is a linear function, not a constant function, so we can use function notation. But we are not talking about the work that is done by the spring itself. If we stretch the spring, then the displacement is to the right. However, if we have the displacement to the right, I'm just going to write the word displacement. The displacement is to the right, but the spring force is the force that, if you let go, the spring force would be acting to the left, because it would be trying to return the spring to equilibrium position. Meanwhile, the hand force, or whatever is causing the stretching, is in the same direction as the displacement. So while the spring force is negative kx, the hand force is going to be positive kx. Okay, so let's take a look at the problem. We are told that the equilibrium length of a spring is 3 meters, and 10 newtons are required to stretch the spring an additional 50 centimeters. Typically for Hooke's law problems, we have information like this so that we can solve for the spring constant k. So we have magnitude of the spring force is equal to kx. I don't want to deal with the sign because I'm only going to worry about the hand force anyway. So we know that equilibrium position is 3 meters, and we want to stretch the spring an initial 50 centimeters, and we have to convert 50 centimeters into meters. And so we know that it's going to require 10 newtons of force to produce a displacement of 1/2 a meter. And as a result, k is equal to 20 newtons per meter. Now, just like in the previous question, we had a constant for g, we had a constant for rho, and this spring constant is also a constant. So now we want to know how much work is done in stretching the spring 5 meters beyond equilibrium. Well, we're going to have work is equal to the integral of a little bit of work, which is either a little bit of force times displacement, because we have the displacement of the spring and the hand force in the same direction. We don't need the dot product. Or we could have a measurable amount of force times a little bit of displacement. In this case, we can see that the force, the spring force, well, let's turn it now to the hand force, is going to be positive kx, which is 20x. And if we are going to stretch for 5 meters, then we see that this force is a measurable amount of force. So we are not going to be dealing with this version of the integral. And specifically, our displacement is just going to be, our ds is just dx, because we're just changing horizontally. So we have that work is equal to the integral of the hand force, which is 20x times dx. And we have, we're going to stretch the spring 5 meters beyond equilibrium. So starting from equilibrium is at 0 to 5 meters beyond is 5 meters. So a quick integral to work out, 10x squared evaluated from 0 to 5 gives us 25 times 10, or 250 joules. In the last example, we have an 800-pound steel beam hanging from a 50-foot-long cable that weighs 6 pounds per foot. And the cable is wound around a steel drum attached to a crane. So we have a steel beam. Myself more room to draw the diagram. We have a steel beam which has a weight, which is already a force, of 800 pounds. And it's attached to a cable which fully extended is 50 feet long. And the cable is going to be wound at the top by a steel drum that's attached to a crane. I'm not going to bother drawing that. I don't know how to draw a crane. Well, before we go any further, we should probably sketch a coordinate system. I'm going to put the y-axis along the cable, and the x-axis I'm going to put at the bottom of the cable as it attaches to the beam. In part A, it asks, how much do the steel and cable weigh when the cable is fully extended? So in part A, we need to know how long is the cable when it is fully extended, and how much is the weight of that. And we need to know how much is the weight of the beam. Does the beam's weight change when it's at different heights because it is being lifted up by the crane and the cable? No, the beam will always be 800 pounds. So the total weight, which is going to be an FG, is going to be the constant 800 pounds of the beam plus 6 pounds for every foot of the cable, which when fully extended is 50 feet. And just by looking at the units then, we can see that we're going to get 6 times 50, which is 300 pounds plus 800 pounds is 1100 pounds. Again, this is regular multiplication here instead of integration. We don't need to integrate because the 6 pounds per foot is a constant. And so whenever we have a constant multiplied by the distance, that's just regular multiplication. We need a definite integral whenever we have a non-constant function times, in this case, the 50 feet. Okay, so in part B we are asked to express the weight force F of the steel and cable system as a function of the length of cable y. So we are told that we are going to let y be the length of cable. So when the cable is fully extended, y equals 50 feet. Let's just write this down. Fully extended implies that y equals 50 feet, and fully wound, so that the steel beam would be lifted to the top, means that the length of the cable extended is now 0 feet. And so we have the length of the cable is this amount of cable showing. So then to express the weight force F of the steel and cable system, we know that the 800 pounds is constant, and we are going to get 6 pounds per foot of cable that is exposed. And the number of feet of cable that is exposed is called y. So then we're going to get the weight as a function of y to be 800 pounds plus 6 pounds per every foot of cable, which is y feet of cable that is exposed. Okay, so now in part C we actually get to the calculation. You wouldn't be given parts A and part B as stepping stones in an exam type question. Part C asks how much work is done in lifting the beam by winding the cable about the steel drum at the top of the crane for the first 20 feet. Well, in the first 20 feet, let's actually go back to basics. We know that work is equal to the integral of a little bit of work, which we've got the lifting of the beam through by the crane, and we have, so this is the force by the crane, which is going to be equal and opposite the FG force. Here, technically, I'm dealing with the magnitude of the FG force because I'm not dealing with the direction of this force, which is at 270 degrees, which would give it a negative y component. So we're just talking about the magnitude of the weight force, which is the same as the magnitude of the crane force. There's no need for the crane to accelerate the beam as it lifts up. We can simply lift the beam at a constant velocity, which means zero acceleration, which means balanced vertical forces. All right, well, the integral of a little bit of work can be the integral of a little bit of force times displacement. Again, our displacement is in the same direction as the force of the crane, so we do not need the dot product. Or we could have the integral of a measurable amount of force times a little bit of displacement. As we see, we have already found that the magnitude of force of the crane is 800 plus 6y, because y is length, it is a positive quantity. And so we will not be using the df version of the work calculation. So we have the weight is f, or 800 plus 6y. The displacement is going to be dy, it's going to be a change in y. And the only other thing we need to concern ourselves with are what are the bounds of integration, the values for y for the first 20 feet. And I'm actually going to leave you to try parts 1 and 2 on your own based on whether we want the first 20 feet of work or the last 20 feet of work. So give those a shot. This concludes section 7.4, work. Please ensure that you've completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.